should we put our videos off?
Okay, I'll just start the session now.
Yeah.
So, hello everyone. Welcome to IIB special lecture series with JSW Steel. So, today's session will be moderated by Dr. Harshvardhan Subbarao. And to begin today's session lecture series, I would request Madam Ruhi to please play a small introduction video on IIB.
Yes, Deepika.
Thank you, Ruhi. Now I'll request Ms. Purnima to please present the video on JSW.
India, a nation powered by 1 billion dreams. Dreams that we aspire to fulfill every day. Together with our collaboration and commitment, as India embraces to be a $5 trillion economy by 2025, we are all geared up to be a part of this monumental journey to usher in a brighter, better future. Together, we touch ordinary lives and make that difference. We better every day. Together, we make steel that you carve into your agri-equipment. Together, we sow the seeds of success. We make steel that gives the grit and grind to your heavy equipment. Together, we change the landscape of our country. We make steel that you beautifully mold into your automobiles, just to drive our nation on its path towards prosperity. We make steel that you transform into solar energy. Together, we steer our nation towards a greener tomorrow. We make steel that relays your transmission lines, just to brighten the future of millions. We make steel that styles your appliances. Together, we bring happy smiles. We make steel that adorns your development projects. Together, We provide shelter to millions. We touch lives, make them better together, every day. We empower communities, make them better together, every day. We nurture dreams, make them better together, every day. As India embarks on its accelerated growth journey, we are firmly placed to leave our mark in it. Together, we touch millions of lives and make them better every day.
Thank you, Purnima. So our today's session is moderated by Dr. Harshvardhan Subbarao. I'll just give you a brief introduction on him. Dr. Harshvardhan Subbarao holds a PhD in steel structures from Imperial College London and MS Engineering from University of Michigan. He has been designer of a number of landmark award-winning projects such as Signature Cable Stayed Bridge, Delhi, 4.56 kilometer rail cum road bridge, Patna, bridge number 20 on JURL, metros, viaducts, elevated roads, cable stayed, arch and extra dosed bridges, underpasses, etc. He is vice president of IABSE Zurich and member of its technical committee and past chair of its bulletin edit board and serves on several committees of IRC, BIS, IABSE, and FIB, Highway Research Board of India, and various international and national bodies. He is a member of BIS Apex Committee CED 7 for steel structures and sections, was a committee member of IS 800 Limit State Code, and co-convener of IRC Steel and Composite Bridge Committee. He has over 30 years of experience and serves on various international and national specific and technical committees, editorial boards, and has a number of papers, publications, and bridge projects to his credits. Thank you, sir. Now I'll pass on the session formally to begin with. Thank you.
Yeah, good evening, everyone. This is actually the last in our series sponsored by JSW for the IIBE and focusing on steel bridges. And in this last day today, we thought it apt to focus on sustainability. The issues of decarbonizing steel bridges is the topic on which Mr. Hegde will be speaking to us today. You are in for a treat, I assure you that. I know him to be someone of a very thorough ability and presentation capabilities, very good speaker, and you're in for a treat, I can assure you that. Mr. Vinay Pandey, at the outset, I want to thank, as you're representing JSW, I want to thank you all for the support you all have so kindly shown to IIB all along, and helped bring this series to a good focus. And today, Mr. Hegde, our speaker, will be speaking on this topic, decarbonization of steel bridges. Mr. Hegde is having his own recently formed company called Decon, Design and Construction Consultants, Complete Solutions, Decon Complete Solutions, and he was former CEO of Stoop Consultants and an executive director of Gammon India before that. And he has more than 35 years of experience in the construction sector in design, technical management, project management, contract management of all kinds of highway bridges and different types of structures, as you see. He's a recipient of 9 national recognitions, in addition to an international prize and of various institutions like the IRC, ICI, NDRF, IBC, and IABSC. He has more than 140 publications to his credit as a member of various IRC and BIS committees. He's also a member of TG 10.1 of the FIB, which is a special task group working on the FIB Model Code 2020. Apart from being on technical board of ICI and academic board of SPC, Sardar Patel College of Engineering, he is also a fellow of the Indian National Academy of Engineering. I know Mr. Hegde for many, many years. In fact, we are of the same age. And whilst he has white hair, I have little hair remaining, but I still have some more which are black. So on that note of friendship, I'd like to start this presentation today. Only I will introduce first the other persons who will be our special panelists today. I hope Professor Arul Jayachandran is able to join. I'm not sure, he's overseas. And if he's well enough, he will join us. But typically, he's professor at IIT Madras, and he did his PhD also from there, from IIT Madras. He's a specialist on steel and steel composite bridges and buildings. He's a convener of the IS 800 code, IS 801 code form sections code, and so many others in the B5 committee for IRC for steel bridges. Is published widely in national and international journals, guided a number of PhD students for earning their PhD, and is also an associate professor at Georgia Tech in the USA, Georgia Tech, Atlanta in the USA. And he's also in Australia, he's a senior research fellow at the Wollongong University of Wollongong. He loves hockey. He has captained the Madras University and IIT Madras in hockey. Apart from research and teaching, Arul mentors students with psychological counseling. And anybody who has heard him speak knows that he's a phenomenal speaker. So that is one of our expert panelists. The other also professor is Professor Siddharth Ghosh. He's he's the Jitendra K. and Meena J. Mehta Chair Professor of Structural Engineering at the Department of Civil Engineering in Mumbai, IIT. Professor Ghosh's illustrious academic background includes a B from Jadavpur University. He then received his master's from IIT Kanpur, and he finished his PhD from University of Michigan in 2003, the same place I did my master's too. And we share that. He joined IIT Bombay, and he has been there, holding various academic positions in the last 2 decades, and especially in the Center for Promoting Steel and Developing Steel and Steel Technology and steel itself as a material. They have a center of excellence, which he's very much involved with in IIT Mumbai. His research interests include probabilistic methodology in civil infrastructure risk reduction, and he supervised students in structural health monitoring, analysis and design of tensile membranes, risk analysis and earthquake engineering, uncertainty quantification, and use of topology optimization structural design. And he manages the structural safety risk and reliability lab at IIT Mumbai. Currently, he is with the Bureau of Indian Standards for Tensile Membrane Structures and Structural Health Monitoring on those. He's the convener of both those for the Bureau of Indian Standards. And he's been appointed recently as the Dean for Educational Outreach at IIT Mumbai. So that's Professor Ghosh. And then we have, of course, from the industry, Mr. Mohanty, he's probably one of the finest fabricators and persons who understands steel as a material, steel as a fabrication, and steel in use. He's a brilliant person, and he's done his BSc in mechanical engineering from NIT in Roorkela. But he has done all kinds of work in steel and stainless steel, erection, handling. He's a fountainhead of knowledge. If you go to him with a problem, you're sure to get a solution. Anything to do with steel, he's the one-stop shop. And I would like him to have been involved today because he's been with us in the steel world for many years and helping us along, especially with issues of fabrication and erection and things like that. So on that note, with these as our panelists and such an eminent and expert panelist group, I would like to start this session by inviting Mr. Hegde to make his presentation on the virtual platform.
Thank you. Thank you, Harsha. You are able to hear me? All of you? Yeah. Absolutely no problem. My screen is visible. Yeah. Thanks a lot. And that was an excellent. In fact, I'm very grateful for you for that introduction. And as you rightly said, that we go long back, and we have been friends, especially in this cause of sustainability, as well as latest ultra high performance concrete. Also, we have been discussing and working together. Coming back to today's topic, I've chosen a topic that's a decarbonization of the steel bridges, particularly the steel bridges. Before that, I would like to give some sort of background to that. What is this decarbonization all about? Why we are talking about the decarbonization suddenly, and how it is related to the climate change. And after having given a proper background to that, I'll just come to this subject of the particularly steel structure, steel bridges, how to decarbonize, by what time this decarbonization can take place. That is the whole presentation is all about. In fact, some of the slides I have taken from Dr. Harshavardhan Subbarao also, who had made a presentation in recently held with World Steel Conference, like in Delhi, all of us were a participant, and there also, good to see Professor Siddharth Ghosh was also there in that particular international conference. Now, all of us know by this time, including perhaps Mr. Trump, that the climate change is not a myth anymore. Like that's a reality, and it has come to plague us, even in India, quite often by way of cyclones, by way of avalanches, by way of floods, and the precipitation patterns, which is not normal, basically the abnormal precipitation patterns. And in over the period, especially after the pre-industrial era, the carbon dioxide concentration, started increasing. It has increased by 410 ppm, and alarmingly, in last decade, at the rate of 2.5 ppm, it has been increasing. Before that, it was increasing only by 1 ppm per year. That means this concentration of the carbon dioxide in the environment, I'm just going to explain that later. Actually, what is doing it? It's increasing it is what they call it as a global warming. All of you are aware of it. This global warming, if it is more than 1.5 degree by say 2015, I think perhaps this world will not be there. Like the 3 degrees. Suppose if it goes to the 3 degrees and all, we can safely say there will be apocalypse on the basis of the manifestations of this climate change, which is taking all over the world in the form of precipitation patterns, floods, droughts, wildfires, landslides, melting of ice glaciers, as well as the avalanches, as you can see here. So all of us have to get geared up to that, and how to overcome this problem of like this carbonization, which is leading to the global warming, thereby this disastrous manifestations. How to avoid that? We'll have to work on that. Now, let's have a look at this carbon dioxide emission to the environment. I think the data is varying across the world. Like the different sources give the different data. We are particularly concerned about the construction sector, basically, right? In the construction sector, as you said, it's all, like if you collect the data all over the world from the different sources, and again, if you average it out, what we find is around 12.75% is can be attributed to this construction sector, out of which cement is contributing around 3%, and the steel is also around, say, 2.75% to 3%, and other building materials is 1.25%, and utility, end of the life, beyond the life, around 5.75%. In addition to that, energy used in the buildings for the operation, like for the water supply, for the vertical lift movements, so many things, energy is required for the operation of the building. That is, contributing to the carbon footprint of, when we say carbon footprint, it's the carbon emission to the environment, basically, of 17.5%. So that is how it is happening. And in the world, India is responsible for emitting around almost in the rank 3rd in the world. If you really look at on the right-hand side of that, the China ranks first, and the United States ranks second, and India comes with the 6.6% is overall carbon dioxide emission to the environment. You can have a look at it. Though, but per capita, the carbon dioxide emission as well as the energy consumption in India, as well as the China, perhaps is lower, compared to that of the United States, because our population is very high. So if you look at the per capita, it may not be very high, but if you look at the absolute of the gross carbon dioxide emission, India ranks at around 3rd in the world. I think it's a matter of concern for us. Now, because of this, whole world leaders and the whole thought leaders gathered together. I think it was first in Paris, what it called as a COP 21, and the world leaders committed to reduce the carbon dioxide emission or make it zero by 2015, the COP 21. And the Indian commitment was, as you can see here, some of the commitments were there. But that commitments, which was made in COP 21, was revised in the next meeting which took place in 2021 in Glasgow, that is called as a COP26, where our Prime Minister very famously gave the Panchamrita, like what they call it as a Panchamrita, that means 5 panaceas to carbon neutrality, to achieve the carbon neutrality by 2070. And those 5 panaceas are here, like reduce economies, carbon intensity down by 45%. And he proposed in 2 phases, in fact, by 45% up to the first phase, that is by 2030, and the next complete carbon neutrality by 2070. This is for overall from the Indian perspective. It's not only meant for the construction sector, basically, it's for all. But very interesting and very exciting for our Indian subcontinent is that whatever we had promised in Paris, that is in COP21, we could achieve quite a lot of, we could make progress in the carbon neutrality, achievement of the carbon neutrality, quite a lot. And we ranked among 10 top countries in the world. I think that's a credit. And India is in the right path, and in the right path of achieving the carbon neutrality as promised by, as committed by our Prime Minister by 2017. Now let me give the background, because straight away, before getting in straight away into the how to like decarbonize steel bridges, let us understand what is this, what we are talking about, carbon emission. What does it mean? There are 2 types of carbon. One is called the operation carbon, and another is called the embedded carbon. We'll have to understand. Carbon emission, or the global warming potential, always has been expressed in terms of a kg carbon dioxide equivalent or a ton carbon dioxide equivalent. That means, like the greenhouse gases, carbon dioxide, along with the carbon dioxide, there are other greenhouse gases like CH4 and NTO, etc. But maximum or the majority of this greenhouse gas emission, carbon dioxide accounts for almost around 90 to 95%. So most of us will be concentrating on the carbon dioxide emission rather than CH4 as well as the NTO. That is why we call the emission which has been taking place into the environment, which can cause the global warming. So 1 kg carbon dioxide emission to the environment causes the global warming, has the global warming potential of 1 kg carbon dioxide equivalent. That we'll have to understand. Now, there are, as I told you, there are 2 types of carbon. One is the operation carbon, another is the embodied carbon. Operation carbon encompasses carbon dioxide emission. I'll be talking about the carbon dioxide emission. That is always equivalent to that of greenhouse gas emission. You have to understand that. Energy centric operations in buildings such as heating, cooling, and ventilation and lighting system. These are called the operation carbons. Whatever the lighting system we have in the buildings, and that is called the operation carbon. And this operation carbon normally, which is used for the purpose of the energy, which is used for the purpose of operations of the buildings like heating, cooling, and ventilation and lighting systems, etc. This is the energy which is supplied directly. That energy, only way to reduce this operation carbon is but to go for the renewable energy sources. Normally, whatever the energy we are getting and we are spending right now is from the non-renewable fossilized fuels like the coal, natural gas, and petrol, and particularly coal burning. The thermal power plants which has been producing energies in our country normally use the coal, and by coal burning you produce the energy, and that energy is used for the operational purpose. That is called the operational carbon. So one way of reducing this operational carbon is to replace this non-renewable energy sources into the renewable energy sources like wind energy, solar energy, hydroelectric energy, biomass energy, as well as the nuclear energy. And the extensive research has been going on all over the world, and the debate is going on. In particularly, this energy sector is quite ahead in addressing this carbon neutrality issue all over the world, in my opinion. And there's a lot of debate going on whether how the nuclear energy can be made cheaper compared to that of whatever the energy is being produced by the thermal power plants these days, and how the solar energy and wind energy, all these energies are little bit like expensive compared to that of the fossilized fuel, non-renewable energy which has been produced right now. But the research is going on as to how to make it economical. A lot of work is being done. The embodied carbon is the carbon emissions associated with the 5 main stages of the structures. Basically, we'll have to understand product stage, construction stage, utility stage, end of the life stage, beyond the life cycle. Basically, this embodied carbon coefficient or the carbon factor, when it is multiplied by the quantities, you will get what is the kg carbon dioxide equivalent, which is reduced, which is emitted to the environment. That is the embodied carbon. In most of my presentation today, when you are talking about the decarbonization of steel bridges, I'll be most of the time concentrating on this embodied carbon, because embodied carbon, 50% of the embodied carbon emission takes place at the product stage itself. When you say at the product stage itself, manufacturing of the steel itself, manufacturing about the cement itself in case of the concrete. That if you can somehow control that embodied carbon during the product stage as well as the construction stage, will be able to control or will be able to achieve the carbon neutrality by 2070 as committed by our Prime Minister. And that is our aim when we are talking about the decarbonization of the steel structures or for that matter, the construction industry itself. So what is the carbon neutrality? Now we are all committed to achieve the carbon neutrality by 2070. Let us understand the concept of, I have tried to give here a model of my own here. On the right side, you can see here, it is the estimate, avoid, reduce, and set up, what I call it as. I call it as in years, like EARS. And that is the kind of model. Carbon neutrality is a process where carbon dioxide emission are brought down to this net zero by avoiding and reducing, where avoiding and reducing is not possible by setting off. That is the process is carbon neutrality achievement. Basically, that's how we do it. First of all, we'll have to calculate. Actually, if you really look at, when I say the estimate, we'll have to calculate what is the embodied carbon and what is the operational carbon. That calculation has to be done. Unfortunately, in India, that calculation process is still, has to take place, and there is not agreed or consensus, embodied carbon coefficient or embodied carbon factors, which is there, that the estimation has to be still done. A lot of work is going on. People are working on that. We'll have to do that. Then, once you estimate it and avoid those sort of activities which emits the carbon dioxide to the environment, that is the avoid. But you know that the construction material like concrete as well as the steel is a necessary evil. We cannot completely avoid that. And when it is not possible to avoid that, what we have to do is, how do we reduce this carbon dioxide emission using the same concrete, using the steel? That's what we'll have to work out in the third phase of it. When it is not possible for us to really avoid it and reduce it, as I told you earlier, it's not possible to avoid the concrete construction or the steel construction. It's a necessary evil. For the infrastructure is very much essential for us, and it's a basic building material for us. Avoiding and reducing to a certain extent, we'll be discussing the strategies of the reduction later, but the avoiding is totally cannot be avoided. So which cannot be avoided, we'll have to set off, like those carbon dioxide emissions has to be set off. That is what is called is a whole package of this, or the model is called the carbon neutral model, as you can see over here. There are a lot of standardization in the world. ISO has its standardizations, and there are Euro codes, basically, as you can see on the screen over here, for the sustainability of construction work, assessment of the buildings as well as the civil engineering works. EN 15643 is there, and there is a general framework. Also, there are guidelines, for the framework for environmental performance, social performance, as well as the economic performance. How to calculate, basically the calculation methods for the environmental performance. When you say the environmental performance, global warming potential performance, basically. And there is also calculation method is given in EN 16309 for social performance, and also for the life cycle costing or the life cycle assessment for the economic performance. The calculation method is given in EN 16627, as you can see here. And also ISO as well as EN 15804 has come out with some core rules for the product category, especially the under environmental performance criteria. These core rules for the product category is called environmental product declarations. I think that's very, very important. On the basis of the environmental product declaration, that the green certification, etc., normally takes place. I think that is how it is there. So the standardization is very much there, and these standardizations has come out long back. If you really have a look at it, 2010, 2011, 2012, 2015. So it's been it's a work in progress. The people have been working all over the globe on the standardization of the sustainability since quite some time, with which from the Indian subcontinent we'll have to really catch up with. Also, you see, it can be divided into 4 categories. Actually, this carbonization, especially when you do the life cycle assessment for the economic assessment as well as the carbon assessment, we have to do it at the product stage. These are some of the boundaries which has been decided over here. Product stage has been represented by A1 to A3. Basically, raw material supply, transport, manufacturing. In case of the steel, how steel is manufactured. In case of the concrete, how the concrete is manufactured. I'm talking about concrete as well as steel because it's the major carbon emitting building material which has been used now all over the world, and not only in the world, even in India for that matter. Then the construction process, as you can see here, it is represented by the boundaries A4 and A5. Then U stage is there, end of the life stage is there, and finally the D stage is reuse, recovery, recycling potential has been calculated on this. Now, I also explained environmental product declarations, and that core rules has been, when it is applied up to this, only the construction or the product stage, it is called the EPD cradle to gate. When it is applied from product stage up to the end of the life stage, or even for the matter, reuse and recycle stage, which is called the cradle to grave. That means the product material has been produced and it has gone to its grave, and up to that, both this like environment product declarations as well as the assessment of the economic assessment and the social assessment and the environmental assessment, global warming potential assessment, all this can be done for all these boundaries which has been defined. And there is a code that is a CE, that the guideline is CEN TC 350 that has been available, and it has been extensively used by most of the researchers for doing the research in sustainability aspect. In fact, the same thing I have like converted for a cradle to construction, that is only the product as well as the construction stage. On the screen, if you can really look at it, I've taken the 2 major building materials. On the left hand side, cradle to construction, concrete model, and when the concrete is being produced in the raw material stage up to the production, placement, transportation, as well as the placement, how the carbon dioxide emission takes place, how much energy is required for that energy, again, like when producing that energy, again carbon dioxide emission takes place. All this combined together, ultimately we call it as a carbon footprint. And similarly, in the case of the steel structures, basically the steel structure manufacturing, and then it has to be transported to the yard, fabrication has to take place, different processes has been shown on the screen, if you can see here. Finally, after transportation, that's fabricated material has to be transported to the site, and we do the erection. The entire process, the construction product state to the construction stage, the carbon dioxide emission takes place, also the cost incurred. So the assessment at that stage for both the environmental assessment as well as the global warming potential assessment as well as the economical assessment can be made for both these stages. So we will be basically concentrating on the right hand side model, that is for related to the steel bridges when we come to that. Now, coming to this steel bridges, like that, let us understand how much carbon dioxide emission is taking place because of the steel bridges. I think I've given here a table, you can see here. And in India, for the financial 21-22, if you really look at it, 120 million tons steel has been produced. Out of this 120 million steel which has been produced, 106 million tons steel has been used. Out of this 106 million tons of steel which has been used, around 29 million tons is been used in the infrastructure, especially coming to our topic today. 9 million ton structural steel is used in the financial year 21-22 in India. The 9 million ton structural steel which has been used for the bridges emits around 63 million ton carbon dioxide equivalent, basically 63 million ton carbon dioxide equivalent. And if you really look at it, you have a look at here, actually what I have done, you see, if you, for carbon emission, for producing 1 ton of steel, normally on an average 2 ton carbon dioxide equivalent is being emitted. For producing 1 ton of steel, 18 gigajoule, the energy is required. In fact, it is a very lesser side I have taken, that the energy required for production of the steel is much more than that in some cases. I think the variance are the variance, it is been range is quite a lot. In fact, it is ranging from 18 to even 30 gigajoule. But for the purpose of the calculations, on a lenient side, I have taken 18 gigajoule per ton. And that energy, if you really look at it, 0.1 producing 1 gigajoule of the energy, we require 1 gigajoule of energy. While producing 1 gigajoule of energy, 0.28 ton carbon dioxide emission takes place. That means for using around 18 gigajoule energy for production of the steel, basically we are emitting around 5 ton carbon dioxide equivalent by the energy consumption for the production of the steel. Whereas for the direct carbon dioxide emission, if you really look at it, is 2 ton carbon dioxide equivalent. The energy used for the production of the steel is 5 ton carbon dioxide equivalent. That means the 5 ton carbon dioxide equivalent energy, carbon dioxide equivalent takes place for using the 18 gigajoule gigajoule energy. So the energy used for the production of the steel is almost emitting around 70% of the carbon dioxide. That is the embodied carbon of the embodied energy of the steel manufacturing is around 70% of the overall embodied carbon content. That is a very interesting thing to note over here. And when I'm concluding, I think most of the emphasis by us has to be made how to replace that energy with the renewable energy resources. That is what is very important as far as the steel is concerned, if we want to make the steel the carbon efficient going forward. Now I'll come to what are the strategies to achieve the carbon neutrality in the bridge construction. You see, I explained to you in Paris, that is in COP21 meeting, the agreement which has been done. If you take that the carbon dioxide emission or the global warming potential is 120% by 2021, when we had a meeting in Glasgow, that is the COP26, where all the world leaders had gathered, we had almost reduced this carbon dioxide emission by around 20%, 120%, say for example. I'm just making this 2021 as a reference point where the 100% carbon dioxide emission is taking place, especially in the bridges, structural steel bridges, if we take it. How we can bring it down to this, in case of the structural steel, the carbon neutrality, how can we achieve by 2017? And there could be 6 strategies, as you can see here, which has been noted over here. One is by the design efficiency, saving the carbon dioxide emission through the design efficiency. Second is the circular economy. I'm going to talk about it a bit. And third is the reduction at the production stage itself. Direct emission of the carbon dioxide is taking place while producing the steel. That is around 2 ton carbon dioxide equivalent is getting emitted for producing 1 ton of the steel. That has to be reduced. And also decarbonizing energy. In the sense, we know that energy required to produce 1 ton of steel is 18 gigajoule. If you take it on a lenient side, that means around 5 ton carbon dioxide equivalent is taking place for using that energy, because this energy is coming from the non-renewable resources, fossilized resources basically. So that is emitting the energy when the energy is the carbon dioxide into the environment, when the energy is being emitted to the used for the production of the steel. So that we'll have to see how do we replace that with the renewable energy sources basically. Then we come to the another strategy of basically carbon capture, use, as well as the storage. This carbon which has been emitted during the process of manufacturing of the steel itself, not only for manufacturing, even during the operation also, in somehow, if it's possible for us to capture it and convert into some other chemical or convert some other product which can be used in some other industry. That's how a lot of research is going on. That is also one of the ways of really reducing the carbon dioxide emission to the environment. Of course, in case of the steel, during the transportation, fabrication, as well as the erection, mainly the carbon dioxide emission is related to the embodied energy. Around, I think around 8% embodied energy requirement is there for fabrication, transportation, as well as the erection. That is what my rough estimate is. And again, we'll have to have ways and means to replace that fossilized energy which we are using right now with the non-fossilized energy or a renewable energy. That's how we'll have to go about. So it's possible for us roughly. I think it's not a well-researched data, but it's on the basis of calibrated data, which has the work where the work has been done on other countries. This is my personal assessment. It's possible for us to save, in case of the bridges, steel bridges, especially the 17% by the design efficiency, 15% by the circular economy, 28% by the reduction at the product stage itself, 7% by the decarbonizing energy, and 25% by CCUS and transport and fabrication erection by 8%. By doing that over the period up to 2070, it's possible for us to achieve this carbon neutrality, especially in case of the bridges, in my personal opinion. As I explained to you that what is in our hand, in the civil engineers or a structural engineers hand, or into the professions. Basically, design efficiency is in our hand. Construction processes, including the production and erection, is in our hand. And to a certain extent, circular economy is in our hand. Basically, whatever, comes out of this, and if it can be recycled, reused, and design a structure in such a way that it can be widened later, and those are methods, the circular economy, these are the three things we are in which our hand. Only 30% carbon neutrality achievement, in fact, in our hand as a structural engineer, which I can see. But the rest of the things is that is the reduction during material production. That has to be done by the plant upgradation, by increasing the efficiency of the plant, decarbonizing energy, that is with the energy sector. Or I think our steel manufacturers have to have a captive power plant with the renewable energy resources. That is what the suggestion and the recommendation I'm going to give later. And the carbon capture, use, and storage, I think that has to be really the research has to be done. And again, perhaps that is not in our hand. And only the 30% of the carbon neutrality to achieve, in fact, in my opinion, is in our state structural engineers or civil engineers hand, basically. Now, let us understand that all of you know, I think that the construction is connected. It is not there are a lot of various stakeholders are there: client and owner, architects, PMC, designers, engineers, subcontractors, suppliers, and the standards and code makers. So many stakeholders there in the construction. It's totally connected. Unless all the stakeholders, it cannot be left to the one stakeholder, even including the policy makers. I'll just come to this public policy makers also. All the stakeholders have to be oriented towards the carbon efficient technologies and this commitment of achieving the carbon neutrality by 2070. And all stakeholders have to, it is no more a sort of just a duty, it's an ethical and moral responsibility of all of us to achieve this. Otherwise, our posterity will be in trouble, as I explained to you, because of the climate change which has been taking place. Now, what could be the roles and responsibilities of the owners, engineers, architects in achieving the carbon neutrality? How it can be achieved? basically in the past developing countries like that, they've got a lot of this one, and the mandatory use of, in case of the recycled material from demolishing and construction waste, that cannot be adopted, that can be adopted. Mandatory use of manufactured aggregates, like the slag, from the steel production also normally takes place. The slag is an industrial byproduct of the steel manufacturing. Basically, that slag has to be used as much as possible. In fact, in the concrete itself, up to 85% that slag can be used. And there are slag aggregates also. Basically, that can be used. Recycling glass residue as lightweight aggregate, a replacement of OPC with mineral admixtures like slag. I said slag is an industrial byproduct of steel making. Going for the HPC, HSC, high grade steel for enhanced sustainability, self-compacting concrete, UHPC along with HTS, design build concrete type. In the design build contract type, it is possible for us to do the value engineering as well as the carbon value engineering, which I am going to propagate in the next slides. And very, very importantly, the role of the owners as well as the architects who has been preparing this DPR for that matter, architects and the other engineers have to specify the limits for the carbon dioxide emissions and the energy consumption in the contract itself, if this with the stringent penalty clauses for exceeding the same, and also high rating, that the QCBC methods which has been used for the contracting, the procurement has to have the carbon footprint as one of the major criteria. A lot of emphasis has to be given on that. That is how the owners as well as the architects and the detailed design, the DPR consultants, and also the contract formulators have to really, they've got a lot of things to do as far as this is concerned. Now, as I told you that you see in a concrete construction, if you want to achieve the carbon neutrality, one of the ways of achieving the carbon neutrality is replacing the cement by the mineral admixtures. I said that, like the cement in a concrete, 1 cubic meter of concrete, if you really look at it, cement contributes to 90% of the carbon dioxide emission. Basically, the carbon in the environment, as you can see here, by way of replacing this OPC, that the ordinary Portland cement, with mineral admixtures like fly ash as well as the slag. And the slag is the industrial byproduct. Why I'm talking about the slag here is slag is an industrial byproduct of the steel making. We are talking about the steel decarbonization over here, and it's possible to replace the OPC in the concrete by around 85% in the world, even up to the 85% in the world it has been replaced. I think also nowadays we are allowing, even in the IS 383, the use of slag aggregates. I think it's been permitted only 10% replacement of the natural aggregates. I think we should allow up to the 30 to 40% of the slag aggregate, and also slag has to be processed in the plant itself in such a way that it can be used in the concrete production. So only thing is the debate is going on for the carbon credit for this. I know, like use of slag, whether it has to be given to the steel industry or to the concrete industry, the debate is on. But I think it's a byproduct of the steel. I think perhaps it's better to give the credit, in my opinion, to steel manufacturers over here. Another thing is the designer's responsibility by value engineering during the engineering as well as the design. Normally, any project for that matter, when you are creating a value, the value of a project is created at the design and the engineering stage itself up to the 70%. And there, when the value of during this design engineering itself, normally if the value engineering can be done, up to 10 to 15% saving is there, 15% of the 17% of the cost can be reduced. Similarly, this concept of value engineering at the design stage can be expanded to this, even the carbon footprint reduction, also what I call it as a carbon value engineering. In fact, luckily for us in the construction industry, when you make these structures economical by use of the value engineering, by adoption of the value engineering, automatically the carbon value engineering also takes place, because the whole idea of value engineering is to reduce the mass of the product itself, mass of the building material itself in the project. If you are able to reduce the building material quantum itself in a particular project by value engineering, I think we'll be achieving the carbon footprint reduction or to a large extent. This is one of the ways, and we'll have to emphasize on carbon value engineering going forward. It's not just value engineering for reducing the cost. That's very, very important in my opinion. Let us look at some of the sustainability characteristics of the steel bridges. There's a lot of myths as far as the steel structures are concerned. They feel that it is not durable structures. They feel that it is not an elegant looking structures, and also sometimes it's all maintenance prone. It requires a lot of maintenance, and but the facts are the statistics all over the world, not only in India, proves other way around. If you really look at some of the bridges which has been lasting for a long time in India, the Abdul Bari Bridge, it is a bridge opened in 1862. The steel bridge, I think it's a double-decker bridge, as you can see here. It's still serving the purpose. It's a railway bridge, of course. And then Old Naini Bridge, opened in 1865. It is still serving. More than 150 years, it has been going strong. I have not come across any precious concrete bridges which has been serving more than 100 years. Of course, precious concrete technology has not evolved. It's only evolved in last 60 to 70 years. It has not seen the test of its time. But still, if you really look at it, some of these bridges which has been lasting for a long time. Another bridge is Malaviya Bridge. There are many bridges in Bihar as well as the UP, especially the railway bridges. In fact, it's a double-decker bridge, as you can see here. Multimodal transport bridge on a single same substructure as well as the foundation, as you can see here. Another is the Pamban Bridge in Tamil Nadu, opened in 1913. So some of the myths has been, if you really look at it, those bridges are sort of exploded. That the myths are myths only. They're lightweight structure, long lasting, easily maintainable, service inspectability is easier, rapid and efficient construction is enabled, ease of dismantling and reusing their materials is possible, reliability and redundancy is possible, reduced waste and pollution in case of the steel structure construction, long span construction. I think I'm going to show some of the slides. Quality and predictability is certain in case of the steel construction. So it has been long lasting, and it's a highly sustainable characteristics these steel bridges have, if you really look at it, compared to that of its counterpart concrete bridges, if you really look at it. And also, see, some of the studies which has been done by Garg et al. He studied the bridge collapses during the construction, as you can see on the screen over here, from 1977 to 2017. It is interesting to note, out of the studies which he has conducted, 86% of the bridges which collapsed during the constructions either were RC bridges or precious concrete bridges, whereas steel bridges only around 13%. In fact, was the steel bridges during the construction. That too because of the collapse of the scaffolding, basically. And it is not that there are not steel bridge failures during the construction, as you can see here down. This is a cantilever collapse when the concreting is going on, but the scaffolding collapse, particularly over here, this is because of the overloading at the right hand bottom. But it looks like from the statistic that the steel bridges are less prone to the accident during the construction compared to that of its counterpart RCC as well as the concrete bridges here. So it's less accident prone, which I can see here. Also, it enables long spans compared to that of RCC as well as the precious concrete by virtue of its high strength weight ratio and also the high ductility, perhaps. Most of the categories, if you really look at it, world record holding bridges are in steel, steel as a building material in case of the bridges. This is a Canacal bridge, a 1915 bridge, which is called as Turkey. This is of 2023 meters span, record holding. Rusky Bridge, it holds the record right now for the cable stay bridge. Quebec Bridge at Canada, 549 meters. It's a cantilever bridge. Basically, its records holds the record for the cantilever, longest cantilever bridge. Arc Bridge in China of 552 meter. And this is also holds the record for the arch bridges. This is not a composite arch. This is a steel, pure steel arch bridge, as you can see here. And also this, surprisingly, extra dose bridge, what all of us understand that the extra dose bridge is, that can be constructed using only the concrete, pre-stressed concrete, particularly. If we really look at it, even for the extra dose bridge, the world record holding a 312 meter long extra dose bridge, which is constructed in China, that is again post the record. It's a double-decker extra dose bridge, as you can see here. And even for the hybrid bridge, when I said it's a hybrid bridge of the combination of the cable stay bridge as well as the suspension bridge of 1.408 meter span, again it is made up of steel. Again, this third phosphorus bridge is a road cum rail bridge in a different manner, in the sense roads as well as the rail traffic on side by side rather than on one top of the other. So if you really look at the world record holding bridges in any category for that matter, whether it's the suspension bridge, cable stay bridge, or the cantilever bridge, arch bridge, even the extra dose bridge, including the hybrid bridges, it is in the steel material has been used over there. One of the advantages of going for the long spans, especially in the creeks, seas, as well as the river, is it reduces the foundation. And the studies show that the foundations as well as the substructure in the rivers and the creeks are more highly carbon intensive. As such, not only highly carbon intensive, it's highly uneconomical also. As such, it's necessary to reduce the foundation. So the spanability or the ability to increase the span by using the steel structure reduces the foundation. As such, the carbon emission to the environment also gets reduced, and it helps in achieving the carbon neutrality. Another myth is the steel structures look ugly, like the trusses and those sort of things. It's possible to have wonderful bridges, elegantly looking bridges like Namaste signature bridge at Delhi. I christened it, or I named it as a National Namaste signature bridge because it has a, like a Namaste pose welcoming the onlookers on the bridge, and it is a signature bridge. It is in the national capital. That's why it can be called as National Namaste signature bridge, and it reflects the local culture as well as the tradition, and in its visual form. And also another bridge, Atal Bridge, which has been inaugurated by Mr. Modi recently in Ahmedabad. If you really look at it, the kite culture of the Ahmedabad, it's reflecting. Another bridge which is at the bottom left, the Deccan Footover Bridge in Pune, the Punite Pagadi, it is Pune Peta, which they call it, reflects that. The third is that the Sambhaji Kanpur Footover Bridge, again, which will come up in Pune again. It reflects the Tanpura, Bal Gandharva Hall is nearby to this, where Bal Gandharva used to sing and Tanpura used to be played along with his singing. That sort of cultural reflection is there. So the steel structure, steel bridges could be highly elegant and aesthetically pleasant. Something is there in the aesthetic as well as the elegance that always is associated with the sustainability. I'm not able to really pinpoint that what is that awe factor which makes the aesthetically looking bridges more sustainable. I think it is some relationship is always there between the aesthetics as well as the sustainability, though it is not possible to really quantify that, in my opinion. As I told you, maybe that less accidents are taking place during the construction in case of the bridges, but it is not, though it is less, many accidents are taking place because there are not sufficiently trained designers in the market, and somehow like this academic institutions are not giving much importance to the design and construction of the steel structures, and that the number of credits in the engineering colleges are quite less. It is always the emphasis is given on the concrete structure. Perhaps there's a need for us to look into this the engineering subjects. The academia has to concentrate on that. Another aspect, as far as the concrete is concerned, even the concrete production is a concrete technology that has been well taught in the universities. But when it comes to steel, it involves the fabrication technology, and the steel is already prepared and given. And the composition of the steel, manufacturing technologies of the steel, I think perhaps the structural engineers also has to be taught with. Presently, the fabrication as well as the processing of the steel manufacturing is only taught to this mechanical engineers, if I'm not mistaken. Perhaps there's a need for us to strengthen the education in case of the steel designing, steel fabrication processes, as well as steel making itself. Like if it can be taught extensively in the engineering institutions, and also we can train professionally the steel designers. I think it will be going a long way in really stopping these accidents which has been taking place, though it's not as much as in the concrete concrete bridges. Another aspect is the double-decker structural systems for the decarbonization. Whenever you are going for a long span bridges all over the world, especially the Chinese, if you really look at it, we have Bogeybill Bridge and also the Patna Bridge, which has been talked about while Dr. Harshavardhan Subbarao was being introduced. There are a number of double-decker bridges, in the sense multimodal rail as well as the highway are run on one single bridge, which is on the same foundations. I think it's a more sustainable way to go about it. I think the steel as a material enables it much better than concrete. I think from that point of view, it's a structural system for the double-decker system. In recent years, even the cable stay bridge, which is under the construction, that is Changtai Cross River Bridge, it's a double-decker bridge, which allows rail traffic as well as the road traffic, and it is going to be 1176 meter, which is going to break the record of Rusky Bridge, which is under construction. Whatever the bridges which have been constructed in China these days, the long span bridges, most of them are double-decker. I think it makes sense. And for me, it is inexplicable that the Trans Harbor Bridge, like this Trans Harbor Bridge, which has been going on in Mumbai for almost 10 kilometers, it doesn't have a double-decker bridge. I think it would have been a very good idea to have a double-decker bridge. I'm sure it's a highway bridge right now, and after some time, the public policy makers will have to come out with another metro line over there. Whole work of the foundation has to be repeated. I think it's the policy makers also has to be, oriented towards the carbon neutrality. In nutshell, I would like to say that it gives the better option for the double-decker system for the bridges, this steel. I think from that point of view, it's a more sustainable construction material. In China, again, the art form has been, especially the composite art, in the sense the concrete filled hollow section. These are, it's wrong, the arch bridge, which is holding record for the longest span arch bridge in China, in the world, in fact, of 575 meter. This kind of long span arches is made possible by use of these concrete filled tubes, basically, that with the high tensile steel tubes filled up with the high strength concrete, high performance concrete, which has been filled up, and the spanability is increasing. Going forward, I think it's not only 575 meter, now with the advent of this ultra high performance concrete, also the steel of the strength of 1000 MPa, perhaps the combination of these two will lead to the much higher span arch bridges with the CFT, the concrete filled hollow section tubes that I can see. So this kind of the structural system with the combination of the ultra high performance concrete as well as the ultra high tensile strength the steels will give a lot of sustainable options for the steel bridges too. This is for the bridges, buildings. I'll just skip this slide. Even in the buildings, the composite columns, which has been extensively used in Japan, with the combination of 150 MPa ultra high performance concrete as well as 780 MPa high strength steel, and it's possible to increase the space inside, and the facade area is reduced, and so many advantages are there. Sustainable options is there, but I think it's in the buildings, it's not in the bridges, so I'll just skip. How these designers can save by the design efficiency by use of very high strength steel, concrete to reduce mass, different types of the steel, stainless steel, weathering steel, high strength steel, and the detailing category of the fatigue. Like if you're going for a welded connection detailing category, normally the section requirement is high. I think perhaps as far as possible, it is better to avoid the welded detailing categories, and it's better to go for the bolted detailing categories where the sections of the steel section can be reduced, and the standardization and modular construction for waste reduction and the fast construction can be used. Pre-stressing steel bridges to reduce the quantum of the steel. I think it should be explored more and more going forward. In the pre-stressing can not only be used for the concrete, can be also used for the steel trusses. I think going forward, we should use that options. Use of composite construction, I explained that. Designed for future upgradation, widening as well as the reuse, optimizing the connection details, detailing for better sustainability as well as the durability, improved correction protection, adoption of the orthotropic floors for the decks and the pylon shells. When the pylon is made up of steel, even the shells of the pylon can be made with the orthotropic plates, as the orthotropic plates are found to be less quantity-wise requirement is less. The carbon efficiency by high strength steel is not a new phenomena. In fact, if you really look at it, I think if, I don't know whether Mr. Ghoshal Saab is there, it has been taken from his book, The Howrah Bridge, which was constructed in 1943, by using the high tensile steel, shifting over to high tensile steel from the original design of a normal steel of 250 MPa. It seems to have achieved 10,000 ton steel reduction, the reduction in the steel itself. Similarly, in the second Hooghly Bridge, 450 meters span, 57 meters span for the pylon, as well as the composite deck construction, the high tensile steel has been used. So the high tensile steel has been continuously used. Another option, especially in the coastal area, where if you want to use the durability of the concrete, I think perhaps it is better to go for the stainless steel. One of the example of the foot over bridge you can see here, which has been done in Visakhapatnam. I think the MORTH is coming up with a policy to make use of stainless steel mandatory in the areas close to the sea. That seems to be a good option from the carbon footprint reduction point of view, especially from the maintenance requirement is less, and from that point of view. But only thing we'll have to be watchful is for producing the stainless steel. I think the energy required right presently using the current state of the art, energy required is 50 to 60 gigajoule per the ton of production of the stainless steel. But unless this energy requirement energy is replaced with the renewable energy sources, I think it carbon intensive wise, I think it's not going to be carbon friendly product. Only from the maintenance point of view it may be, but unless this energy requirement is replaced with the renewable energy sources, it is going to be carbon intensive. The stainless is going to be carbon intensive. Other option is the weathering steel. I think if even by going to the weathering steel also, it's possible for us to really reduce the maintenance requirement, and normally the dense and sticky the layer forms, whether rust forms on the top of this kind of steel, and it will be taking some time for the formation of this steel. This rust resists the ion penetration into the steel and initiation of the corrosion process. And this bridges can be designed even up to, in my opinion, up to 150 to 200 years with the weathering steel. But the thickness, the rust thickness requirement may be more. Accordingly, it has to be designed. There are some examples which has been done in 1989 in Okuso Bridge, as you can see here, and also the Constance Cycle Bridge, which has been done. There are several examples. One of the examples in the initial stages, this rust formation may look non-uniform, but over the period, like if it becomes a dark brown color, as you can see here in the right hand top corner of the slide over here. Another carbon efficiency technologies, the modular bridges, which has been discussed in our B5 committee. I think it's good that the convener of the B5 committee, Mr. Puri, is among us today, and we will be able to bring out this also. It enables very fast construction, reduces the wastages, and when it enables the fast construction, normally the traffic congestion is reduced. Traffic congestion will not be there at that particular area. Traffic blockade will not be there for a long time. And in this particular cases, modular bridges, the panel bridges are faster modular bridges to assemble and simple to launch. The span can be in multiples of panel length, and it can also be said to be the carbon efficient bridges. And there are patented modular bridges, like one is Acro, and there are several, many in fact. Also, the steel in the decks as well as the pylons, as I told you, can be reduced by going for the orthotropic plate system. As you can see here on the right side, in the transverse direction as well as the longitudinal direction, they will be having a different the properties. Basically, when you say the orthotropic plate, over here you can see here, this is a longitudinal girder, this is the cross girder, as well as again there are several longitudinal girders over here. It's possible to reduce this the weight of the steel. When the weight of the superstructure is reduced by turn, the foundation weight is also reduced, and it is possible to have the carbon efficient solution by use of this orthotropic plate solutions too. And in my opinion, most important thing is the role of the standards and the code makers in decarbonization. In case of the steel bridges, I think particularly, I think it is B5 committee which comes into the picture. They have been bringing good guidelines. The tub girder guidelines is going to be approved by the council shortly. And there's a need for even the extrudos as well as the cable stay, especially the cable stay, where I think the composite girder for the long composite deck for the long span cable stays invariably it is required, especially when you're going beyond 550 meter span. The cable stay bridges are normally economical, not only economical, even carbon efficient with the composite girder deck. In fact, beyond 700 meter, you will have to go for the orthotropic plate deck, which is steel, and on top of that, as I explained, you will have to have the wearing course, which is directly laid on top of the orthotropic plate. And that's how normally the work is done. And very important is the review of safety factors to make the structures less carbon embodied. The safety factors as well as the load factors, which has been used for the concrete, need not be used for the steel structures. Basically, if you really, what are the safety factors? When you talk about the load factor, it is possible in the concrete material. As a material, the variation in the density is possible. Variations in the imperfection, casting imperfection is possible. In the when you are using the steel structure, steel plates, the variation to that extent is not possible. So it's necessary for us to really look at these load factors, especially for the steel structure. And also, it's not necessary when you're going for a very high kind of the steel, and when you go for the concept of the pre-stressing of the steel itself, not to specify the span to depth ratios in the steel structures, that will stifle, like the reduction of the quantum or the mass of the structure itself, which is carbon, which is one of the methodologies to achieve the carbon neutrality or the carbon efficiency. Allowing composite piles for the pile foundations. In the pile foundations, invariably, especially in the rivers, we use the liners. I think the liners can be made to be taken, the properties of the liners can be made to be taken into consideration in the design itself, final design itself. Accordingly, the thickness of the liners can be increased, and also we should allow the piles to be designed as a composite section. I think these are some of the methods, the roles, the standards and code makers can permit from the point of view of the carbon neutrality or the carbon efficiency. The codes and standards should catch up with the emerging new technologies and material science very fast for applications. Unfortunately, say for example, this tub girder and the cable stay and the extrudos guidelines, and also another ceiling which you are bringing it out. All these guidelines are taking too much time. And of course, we have done a lot of work to bring out this extra dose cable stay as well as tough girder, which is going to be out. But I think the way the research is going on, the technologies are emerging, and this has to be condensed in the codes and as well as the standards as early as possible from the point of view of the carbon efficiency going forward. And also there is some sort of a the idiosyncrasy among we, including myself. I'll tell you that the workmanship in India is very poor. To take care of the workmanship, load factors have to be increased, and the factor of safeties have to be increased. I think that is not the correct way to go about, especially in view of this climate actions which has to be taken. We have to make sure the workmanship is ensured by providing the factor of safeties as well as the load factors. I think it's not possible to improve the workmanship at the site. I think if the people are not doing proper work, I think those people who are responsible for getting the work done properly, they have to get the work done properly. That is where the concentration has to be there, rather than having an idiosyncrasy. To cover up the workmanship, we'll have to increase the factor of safeties, which makes the structure carbon sensitive, in the sense carbon efficiency is lost by increasing the factor of safeties, as well as it especially I've seen that happens during the codal committee meetings. Sometimes I think it may come even from me, but I think we'll have to get out of that idiosyncrasies. Then how do we reduce this carbon footprint during the transportation, fabrication, and erection? Only way I think is to replace the energy source. I think it's around, I consider it around 8% carbon emission takes place in the steel bridges when you are doing due to the transportation, fabrication, and erection. That is my study, but it may vary quite large depending upon the various studies, and that has to be reduced. That can only be done by use of like this renewable energy, especially the biomass energy and the solar energy. I think wherever it is possible for us to have a solar energy as well as the biomass energy and the wind turbines and even the wind energy, it's possible to get those energy sources to replace the non-renewable energy sources which is being presently used. I think that's the only way to reduce the carbon footprint during the transportation, fabrication, and erection. It's not possible. And also some of the carbon efficient fabrication technologies by use of digital technologies can be used, and renewable energy, I said, LED lighting can be used, reduction in compressed air leak and gas systems can be made, power optimization, use of inverters, new generation well set, hybrid and electric company vehicles for the transportation of the materials inside the casting yard, it's the fabrication yard itself, waste minimization, including the consumables waste. I think these are some of the methodologies which can be used during the transportation. Of course, when the material has to be brought from the fabrication, the steel manufacturers to the site for the fabrication, we'll have to evaluate which transportation, whether by the sea or train or the load is economical and the less carbon intensive. That has to be studied, and we need to have a look at it, and then we'll have to decide that. These are some of the methodologies during transportation, fabrication, and erection can be done. Finally, that I'll come to this circular economy, and look at this steel structure. I think the steel structure is truly compatible with the structural economy models, and because it is recyclable and it is fast constructible, and none of the steel, whether it's a stainless steel or a weathering steel or a normal steel, less strength steels which we have been using, carbon steel, what we call it as carbon steel, and all these steels are recyclable, and it can be used once again. So from that point of view, I think the structural steel as a material is with the utmost compatible with the circular economy models. And here is one of the case. It's a very versatile and a very flexible material by virtue of its high strength to weight ratio and also the ductility which it has got. Basically, this is one of the examples where the bridge which was constructed using pre-stressed concrete technology, of course, at the state of the art at that particular point of time, has deteriorated over the period. The superstructure started sagging because of what we call it as a creep phenomena, long-term creep phenomena. And it is not because of the corrosion and all, as has been said in many forums. It is particularly because of the long-term creep phenomena. Also, the central hinge, which was in vogue at that particular point of time, and the sagging particular case, and always in a long span bridges, as I explained, that the foundations are more carbon intensive. Not only more carbon intensive, it is highly uneconomical to do the foundations in the river. Here's a particular case where the superstructure, concrete superstructure, is replaced with the steel truss superstructure, as you can see here. So it can be used for the prolonging the life of the existing structure itself, making the existing structure less carbon intensive. So the steel is a highly circular, economical, model oriented, this one. When you're talking about the life cycle assessment of the bridges, whether it's economically or whether global warming wise or the social impact wise, what we are talking about, we have got 4 different boundaries, as you can see here. That's a product stage, that's a material production stage, that's a A1 stage, what we call it as. Then the bridge construction stage, again, it's a A1 stage. That's another boundary. Then the bridge use stage, that where the maintenance of the bridge has to take place, where like the expenditure takes place financially as well as the socially, and also global warming place, all during this 4 stage. Even the bridge demolition stage, which is possible for us to do the assessment, economical assessment, environmental assessment, as well as social impact assessment, as you can see here. Now, during the maintenance phase, or the operation phase, what we call it as, what normally done in the life cycle assessment is, say, for example, here you can see here, this is around in 100 years. Suppose a bridge is designed for 100 years. That is a life which we designed the bridge for in Indian, as per the Indian codes. And if we design the bridge for 100 years, the surface of the deck has to be replaced in 25 years once and the 75 years once. This could be the maintenance regime which you can define is rehabilitation of the deck can take place after 50 years once a rehabilitation of the deck analysis or the life cycle assessment, and a new surface abutment, and say, for example, steam build production. It can be done on 25 years, we can specify 50 years and 75 years. And equipment used, cleaning of the expansion joints, I think it has to be continuously used, as you can see here. Only in 2050, that year it is not done. Otherwise, continuously it is required to be used. When you are using this equipment, normally there is the environment impact, social impact, as well as the economic impact. All assessment has to be done during the operation period, as you can see here. The bridge also normally is designed taking into consideration the average traffic study, average traffic details, as you can see here, in a day, how the traffic fluctuation on the bridge takes place. And over the period also, the traffic forecast has to be done. Accordingly, the number of lanes required for the bridge has been decided. And it has to be decided basically. And say, for example, if your forecast is saying that after 50 years, the bridge has to be widened, and in your life cycle assessment, that widening cost, as well as the widening global warming potential, also has to be calculated over here. And sometimes when the bridge is under the maintenance or the repair, we'll have to study the traffic pattern. The traffic congestion will take place. Because of the traffic congestion take place, there will be an impact, a social impact, environmental impact, as well as the economic impacts. That assessment has to be done. Say, for example, here the work is done over here. This is the approach speed. This is a deceleration zone. This is a queuing zone, as you can see here. Then the road traffic is constricted over here. Because of that, suddenly the acceleration takes place. This is a working zone. The average speed will be very less. Again, the acceleration takes place. And because of this sort of things, there could be an accident. like if it is not properly done, the accident which took place recently in when our Cyrus Mystery was traveling, it was said that it was not designed, the signages were not designed and it was not designed properly. That is why the accident take place. All these things have to be calculated and assessed in the life cycle assessment cost, as well as the life cycle assessment of the carbon. In fact, I explained about this environmental effect impact. Apart from this global warming or the carbon dioxide emission impact, under the environment impact assessment, many things have to be studied. But at this stage, I think it's enough for us to study the global warming thing. Of course, in the economic impact assessment, the initial cost, operation cost, end of the life cost has to be calculated. Social impact, it is the vehicle operation cost, driver delay cost, and the accident cost has to be calculated when you are doing the life cycle analysis, as you can see here. This is just some sort of a broad view on the life cycle assessment, how it can be done. A lot of research is going on all over the world, in fact, and we can take cues from there. In fact, the responsibility of giving a guideline on the life cycle assessment is with Dr. Harshavardhan Subbarao. He has been collecting a lot of information, and we'll have to come out with the life cycle assessment calculator for both the economic model as well as the global warming model. That is the carbon dioxide emission model for that matter. In conclusion, I would like to say that if you really look at the analysis which I showed here earlier, the embodied carbon of the steel which has been used in the bridges is around 63 million tons. Carbon dioxide equivalent being emitted to the environment. This 63 million tons carbon dioxide emission has to be brought to zero as committed by our Prime Minister by 2017. All of us have to be done. From the structural engineering fraternity or the civil engineering fraternity, I can assure that the design efficiency, circular economy, as well as transportation, fabrication, and the erection, it is possible for us to bring down this to the zero by 2070. But my worry is, like this, 70% of the embodied carbon is due to the embodied energy. When I say the embodied energy, as you can see here, 605 ton or 45 million ton carbon dioxide emission is due to the energy used in producing the steel. Basically, 162 million gigajoule energy is required to produce this steel. Unless this energy used during the manufacturing of the steel, by use of the renewable energy source, I think to bring this carbon footprint to the 2070 to zero, or achieving the carbon neutrality by zero, is a very hard task. My suggestion is, one way of going about it, all these steel making plants can have their captive renewable source power plant itself, like that they can use. It could be a solar power plant, it could be a wind energy power plant, it could be any biomass power plant. I think they should plan it. Once they replace it, I think CCUS is working very well, in my opinion. I think they are converting many of this carbon captured carbon into this ethanol, which is going to be mixed with the petrol which is being used right now. And similarly, that can be used in some other places also. That industry is working very well. Only way to go about is, we have to insist upon our steel manufacturers to have their captive power plant to provide that energy, so that they get this energy from the renewable energy sources. With this, Harsha, I've come to the end of my presentation. I'll be able to take the questions as you wish at any time. Thank you very much.
Thank you, Venkat, for a wonderful expose. No doubt you've taken a lot of material from presentations made by others at the World Steel Congress, which I think is important to show and demonstrate what is happening. We were lucky to be there at that event. And a lot of material here are from world experts, really. What has been shown to you today is from people like Helena Gervasio and Luis de Silva, something from my contribution, something which I've taken from the Japanese. So Venkat has some work of his own, research of his own, and all this he has stitched together today to make a comprehensive presentation on where we are, where we need to go, how to achieve that in a broad framework. That is not to say that we have discussed threadbare anything at all. We have just scratched the surface. For example, we don't have a carbon calculator, which is yet. In fact, the world does not.
Yes.
My friend Luis has just been commissioned, or is in deep discussion, Mr. Pandey knows, with the World Steel Organization to develop such a calculator. Some of the problems that lie in this area are these. Say Tata Steel makes one particular type of rolled beam, ISMB beam, and the same ISMB beam is made by another manufacturer. Just to put things in perspective, the environmental product declaration for both will be different. And the world database that we use, the EcoInvent database of this Serra company, the EcoInvent database, where we use that 0.0028 carbon equivalent value and then multiply into tonnage, etc. That database, Serra's database, EcoInvent database, is an average value database. So all the steel fellows in India are all averaged into that one type of ISMB 200, EPD. The value that is an average EPD. Whereas actually it has to go to each product to have its own environmental product declaration, and then there will be competitiveness. Once there is competitiveness amongst the steel manufacturers, the 70% of embodied, which we are talking about, starts to really get addressed. The people who are doing this today in the world, everything comes from Norway and Sweden. Everything starts from the north of Europe, and then it comes down, and they are way, way ahead of all the other manufacturers. They've switched the method of manufacturing steel to a more environmentally friendly method. In fact, in India today, many of our steel manufacturers, and I hope Mr. Pandey and others are listening to, we need to move away. We need to get into electric arc furnaces. That is the first step, the first killer step to knock out the embodied carbon in a huge way. To do more than what the entire construction sector can do on its own. Yes. So this is the first step which we are not taking. It is a highly capital intensive. It has got a lot of cost, and there are problems in the steel industry which prevent it from taking these bold steps. But actually, that's where the maximum impact can be done in terms of sustainability for steel. For our part, we are bringing out a coded document in the IRC, which should be out by about the end of this year. Again, this will have the EcoInvent database, and we will be addressing only the average values for every product. And it will be a sort of not a real, nuts and bolts type value calculation. It will be a broad-based calculation, but still it will give you a perspective. If not anything, it will make us more alert, make us more environmentally conscious, will make us more aware to the fact that tomorrow's world, in fact, today's world, why tomorrow's world? Tomorrow is what we want to leave our next generation. But today's world, the world in which we live, already this is a reality. Already the environment product declarations are being done. Companies are scrambling to become, because they will have to realize that manufacturing will be addressed only by this basis. It will not be addressed by any other basis. So will all construction. Contracts will change. The method of evaluation of a submitted bid will completely change. It already is elsewhere in the world. You have to submit your full environmental plan and your whole life cost model. In fact, today, if you have an iPhone with you now, you can just go to the SBRI database and you can use a carbon calculator for a steel bridge. You will see 4 examples there. So it is already being done. And that example is from 2013. Okay, it shows you the entire framework in how to do a carbon calculation for a steel composite bridge. So it is already there. It's on your phone from the year 2013, and Luis has put it there. So it is free for all. So I can share that with you all. Just see the SBRI database. You will get it. I think it is the SBRI database. I'm not sure. I don't remember. But it is there. It is definitely there. And some of the examples some of the data was shown from Luis's presentation. If it is available, I will try and share it. It's apps.apple.com/pt/apps SBRI. If you just type the word SBRI, you get it. Okay, in your app phone right now. So that is where we are today. We have to take a quantum leap in India to catch up. and to start addressing these issues. And I will open up the floor to my other friends after I give you this takeaway note of what is it that we have to really do. The quantification, the assessment, the framework, all that is one issue. But what can we do immediately, in our steel world? Leave alone the manufacturers. As designers and contractors, what can we use and how can we change our framework of thinking? The most favored options, the CEN 350 are the European equivalent to the ISO, and the CEN TC 350 are the ones charged with making all those documents. And when those documents get made by the CEN 350, they go to the Eurocodes or the ISO, the equivalent ISO, they all get used. And then the Eurocodes are framed from these as the background base, just like most concrete codes in the world are framed from the FIB model code. So they provide the framework reference. So that is what is happening in Europe. All those codes Venkat showed you are actually coming up from the work of the TC 350. And those documents are actually free online, the ISO documents. What we need, the most favored option, reduce, i.e. lowering the amount of waste produced. Reuse, using materials repeatedly. Recycle, using materials to make new products. Recovery, recovering energy from waste. The last option, send it to the landfill or to no use. It has no circularity. Safe disposal, but safely do it in a landfill. So let us look at reduce, reuse, recycle, recovery, and landfill as the last option. Steel addresses all these beautifully. It is most eminently suitable for this in the world of bridges. Far, far more eminently suitable than concrete is. So this is what I wanted to just share with you and open up the floor now. Thank you, Venkat, for that excellent, overall framework and overall expose of what is happening and where we need to go and how we might try to achieve it and what is being done in India at the moment. I can start by asking Mr. Gyana Mohanty, a Doyen and a brilliant fabricator and director, and you should see his plant in Odisha. It's something phenomenal. Gyana, can you give us your thoughts on, in fact, some of the slides which Venkat used, which he borrowed from me, are yours. So actually the production one is yours. So go ahead, Gyana, unmute and speak.
Thank you, Dr. Subbarao. First of all, I must congratulate Mr. Hegde for an excellent presentation. In fact, it was a learning. A lot of things I had to, we had broadly discussed, but he put in so many slides. It was very informative. And basically, I'll tell you that the figures that he gave about the carbon dioxide emission as far as the construction sector is concerned, 12.75, 17.5. These are fantastic pieces of information. And he has mentioned so many things. We learned what he has told about operational carbon and embodied carbon. In fact, I'd just like to mention here that because of the Ukraine war, there's a lot of energy crisis in Europe. So what they have done in Germany, they have come out with a circular just to reduce that embodied, that operational carbon. They have increased the temperature limit in offices by 1 degree. But that is the amount of saving can come out of operational carbon. We talked about lighting, we talked about heating, ventilation, and air conditioner. You see, they are very so conscious because now it's an economic reason, but this also contributes to the overall CO2 emission. Then we talked about embedded carbon, replacement of replacing by renewable energy. Here, I'd like to mention one thing. We mentioned about the quantum of carbon that we use in steel production, right? Your figure was we use about 2 tons in direct carbon and 5 tons in embodied carbon dioxide. I'll just give you a figure. In India, we have steel production 2 routes. One is the blast furnace route. Other is this DRI, direct reduction iron route. Direct reduction iron route is a very, very inefficient route. And in India, 46% of our steel is produced by blast furnace route, whereas the world average is 70%. Here we can imagine that what a big task we have in hand. This DRI is what we have: sponge iron plants, then rolling mills, then whatever it is. But question is, we are mostly there for construction sector, because DRI plants do not cater to any other sector like automobiles or equipment and all. They are basically reinforcement steel and structural steel. So construction has a major use of DRI steel, which is a much more inefficient way and much more carbon emitting method than any other industry. So that is one thing which we must harp upon, that we must go over to efficient steel making. That you said that most of the work that is being done in Sweden and Norway, they are of course very, very conscious about their environment. So here in India, we must think about it in a big way. That is, the big plants, they go to the blast furnace route, but this DRI route is extremely, polluting as well as very inefficient. So that is one we have to say. Then about fabrication and erection part of it. Yes, there is a lot of scope. The way we work and the way others have been in Europe, they have been working, the type of automation they have done. These are all efficient ways of saving this carbon emission. We must go into those methods. Second is, we must have to bring in implementation of Kaizens, the way the Japanese do it, and or other methods, so that we do the minimum waste in material handling, whether in the workshop or in the construction field or whatever it is. So there are a lot of scope, although they may be small, but they'll ultimately go to save carbon emission in the case of steel bridges. You also mentioned about use of weathering steel and stainless steel. Well, weathering steel and stainless steel can be an option, but it cannot replace the carbon steel. The reason being, the world doesn't have so much of deposit of nickel and chromium. So we cannot totally replace. So we have to find out better methods of protection so that we can increase the life of bridges. So stainless steel, okay, it needs, the need of that is maybe in the coastal zones, but where there is no coastal zones, their use of stainless steel or weathering steel, which also needs a lot of chromium, while doesn't have so much of deposit. So we have to stick with carbon steel. But then again, we have to think of better methods, better protection, so that we can have more sustainability and durability. These are the most of the things. One thing, Mr. Hegde, you mentioned that the renewable energy, one of the things you mentioned is nuclear. Is nuclear a renewable energy? Do you consider it renewable energy?
Yes, yeah, I think so. There's a lot of discussion going on, especially, even Mr. Anil, what is his name? Karkotkar is also talking about it. What is happening is the nuclear energy, it is becoming uneconomical. That is why they are not using. Nuclear energy is a renewable energy sources. It is not from the fossilized fuels. It is considered to be carbon efficient energy technology, nuclear energy.
Okay, I didn't know about it. But all that idea we have is a fission material, so that the whole thing gets wasted and it can never be reproduced. Yeah. Anyway, experts may think about renewable, but nuclear energy, yes, it's less polluting. Yeah. Immediately, it's less polluting, as unlike our coal-based power plants or other hydrocarbon-based power plants. But then again, having alternative energy sources for the production of steel is definitely a very good suggestion. We should go by that. Overall, your presentation was very informative, and thank you so much for that.
Thank you.
Thank you, Asha.
Thank you, Diana, for your wonderful insights. In fact, on the Trans-Harbour Link, we're using a C5 paint for 30 years. And that itself in whole life cost term, because out in the sea, the orthotropic deck is used, and then the steel is used. Both are actually beneficial on the sustainability aspect, and the whole life cost aspect definitely does come down with these high-grade paints, high-quality, super high-quality paints, which are now being developed. That's a very good comment you made. And to tell us about the DRI, the fact that the DRI is our nemesis, and it's actually in the production side, it has to change. Also, the blast furnace side, also maybe the electric arc would be more. That would also be another thing to consider on the blast furnace side also. So let me go over to Professor Siddharth Ghosh. Siddharth, thanks for joining, and please go ahead with your comment.
Yeah, thanks, Dr. Subbarao. So first of all, Mr. Hegre, a very, very comprehensive presentation. I mean, everybody is saying that, so I don't have to add anything. But if I look at the Q&A, the kind of questions being asked, what is carbon neutrality, what is carbon equivalent, etc., that tells us that we need, first of all, before we take any step, what we need right now is more and more presentations like Mr. Hegre's presentation, just to make the whole network aware that, okay, this is what it is going to be in the future. And I have seen, and I'm sure many of you have seen, a tendency to think that the carbon cost calculation is something of a very advanced situation, advanced calculation. We don't need to worry about that. And people try to somehow avoid that kind of a calculation. But what I can tell you very certainly that, we cannot think of economy in construction unless we think of carbon economy in construction these days. I mean, it's just not possible to avoid that anymore. So better we learn the process and implement it. And finally it's going to benefit us. So I think we also need a positive attitude towards carbon cost calculation, life cycle cost calculation, how to make our construction, how to make our usage more carbon efficient, going towards carbon neutrality. So yes, we need more and more such talks, just for the awareness point. I have few other things, if time permits, I'll go ahead. So what I have seen, and Mr. Hegre has pointed out, that the carbon cost of materials, particularly the carbon usage in construction, is not that significant if you consider the operational cost, particularly for buildings. But this whole thing changes when you come to bridges. See, Mr. Mohanty was also talking about how Germany changed the operational cost by allowing a higher temperature to be set inside the rooms. But we don't have to deal with such operational cost in bridges. So for bridges, particularly, what we will see that the life cycle cost calculation and carbon cost calculation put steel bridges in a much advantageous position as opposed to pre-stressed concrete and reinforced concrete bridges. This advantage also comes out in the fact that when you do life cycle cost calculation for steel and concrete, many times we miss out the fact that the length of design life for these two kinds of structures are very different. So when you're investing on steel, you're investing, let's say, at least for 70 to 100 years, whereas in concrete, our experience with pre-stressed or reinforced concrete has not been so good, right? So that way also we economize a lot in terms of, if you calculate in terms of money, hard currency, if we calculate in terms of carbon cost, carbon equivalent, KGCOT equivalent, both ways we get the advantage of using steel. Finally, I'll say that steel bridges definitely score much better than others in terms of life cycle carbon cost from cradle to grave, and also steel bridges in numbers can change the economic condition, the carbon cost of our construction economy in a big way in a country like India. That's something we need to look at. And Dr. Subbarao started with what we need to do. Yes, immediately a calculator, so that everyone, without going through the theory, without learning from the Japanese and the Swedish, can just use something and get ahead. We need to provide to the everyday user such tools so that it's not something that people would be apprehensive about, but we'll take it in a very welcome way. That's all.
And all the steel manufacturers have to come up with their EPDs for each product.
Right.
Each different grade, each type, and they should come up with their EPDs. That really will be the. So I think they are addressing it. Mr. Vinay Pandey is here. Vinay, can you give us some few thoughts of yours about what is happening in the actual production side of the industry?
First of all, thank you, Mr. Hegre. It's a wonderful presentation. You have collated everything together, and it is really excellent presentation and good insight. The challenge with all of us is, how do we calculate the economic, social, and environmental impact on the life cycle cost of steel while making DPR by structural engineers, as you rightly pointed out. So probably we all have to work together and devise a mechanism by creating some database for life cycle studies, wherein the practicing structural engineers while making DPR can refer to that, and that becomes a standard, and which also gives insight to the policymakers to opt life cycle cost as selection criteria for material and the design. And definitely, Dr. Subbarao, all industries, people are working towards decarbonization, and it is a journey and things. And particularly what Mr. Hegde told, that at least 30% we can immediately address at the user stage through design efficiency and circularity. And the other portion, at least, it is a journey, and then definitely the people are working in that direction. So thank you very much once again. And
thank you, Mr. Pandey. And again, thanks to JSW for sponsoring this series. And this series comes to an end now. Hopefully, Mr. Pandey, we will discuss now that we've raised the awareness, we will go in a larger way. And Siddharth, with the educational side also, we would like to interface with them. So I think it is important to start bring this out to students and youngsters, what we are doing. The awareness, it has to start at the educational stage. There is none. And the awareness, the fact that we have a carbon calculator which you can get on your iPhone is unknown to anyone. I don't think anybody knows it. You just put into your Google, in your iPhone or any phone, you put into it SBRI, sustainability bridge sustainability calculator. That's all you have to put in. And you have a ready-made framework with the EcoInvent database, everything, the step-by-step approach, social, economical, environmental, all addressed. Ecological, all addressed there, and how to calculate. But for that, we need to have a management, bridge management plan. That means every type of bridge, we have to fix the regimes and the epochs of intervention, which we don't do. We go about it in a random fashion, you see. It's a breakdown maintenance approach that we largely follow. To have that, you need to have the maintenance, then you have to get the delay costs, you have to get the user delay cost model, you have to get your interest rate, which you for the whole life cost, you need the interest rate, otherwise, and you need to know the depreciation rate, you need to know so many things to go in there, which we have to work. Then you also need to get your the possible growth of traffic, the projection of traffic, correct traffic, projection of growth of traffic, and that all gets, that means you have to have that available with us for that particular project or that particular crossing. Then you can go into it and you can look at it with steel options, concrete options, pre-stress options in that SBRI bridge sustainability calculator. So it's not only for steel, it's for all bridges.
Yes.
So it's worth looking at, and there you can start to compare steel and concrete options, at least in a play with it, have your own plan, have your own idea, and you would realize that the steel will be sustainable if you go for a 100-year design life, far, far more sustainable in terms of reduced carbon, embodied carbon and carbon equivalent when you calculate. You will see that. Especially on circular, when we address circularity. Someone asked a question about circularity. What is circularity? There is my steel bridge. It's a 350 grade. It's got my I section. I can throw it out and send it back to the melting plant, send it back, or I can cut it from here, go and put it elsewhere. For example, in the city of Mumbai, skywalk at Bandra, which was very beautiful, very nice, was simply sold as scrap, demolished, because the metro was coming there in that alignment. So they removed it from the central verge, the full skywalk, about maybe some kilometer long, more than a beautiful one. Instead, they could have taken the same span arrangement, gone elsewhere, and reused it. It's the same city. We could have reused it. There's nothing wrong with that. So that is an idea of circularity and reuse, and that puts the carbon footprint down like mad, pulls it down quite a bit. So reuse and then repurpose. Today I made it as a residential. Tomorrow I can convert it. It's a cold form decking, and the beam, all beam, steel, everything is made in steel. And then tomorrow I can repurpose it to become a hospital. In COVID times, I convert the whole thing to a hospital, or I convert it to a library, or a change in use, rather than it becomes redundant and it is wasted. As its functionality can be changed, that is repurposing. So these are the issues of circularity. When did this actually gain a lot of currency in the UK? Is when the games for the Olympic Games, the repurposing of their structures, what they call legacy. Legacy. What do you leave after this game? What happens to all these structures? Are they waste? Are they huge places which are no use? So repurposing is very important. And today, the Olympic, the most important thing if you want to hold an Olympic event in your country is to sell repurposing. So it has caught on long ago, and I mean, these are issues which we need to address and deal with without a doubt. With that, there are some few questions, Venkat. If anybody is free to answer if there are any appropriate questions. Let me please explain about circular economy and how it reduces carbon emission. Venkat, do you want to add?
I think you have already explained
Okay.
that.
What is carbon neutrality?
See, the carbon neutrality is actually bringing down the carbon emission to the environment to zero by reducing or by reusing or by avoiding, construction, say for example. But when you cannot avoid, reduce, then offset it by, like circular economy and those sort of things, offset it. To bringing this carbon, to the zero, carbon and emission to the environment to zero. It doesn't mean that, when you're producing steel, carbon emission doesn't take place, takes place. Then you capture it and you reuse it, capture it, convert it to some other, form, product, and that product can be used. So avoid it, reduce it. When you cannot avoid it, maybe set off it or offset it. That is why it is called the carbon neutral. So India is committed to the carbon neutrality. That means carbon emission to the environment to zero, net zero emission, that is called net zero emission by 2070. Our Prime Minister has committed in COP26. That is took place in Glasgow. I think that makes clear. I think Harsha.
Yeah, absolutely. So those fatigue, we can leave that. When the fatigue stress control the design, use of high strength steels may not help much in the reduction of section. It won't be. Siddharth, you want to go?
I think Harsha, you have to answer that.
Yeah, I think you should answer that. Yes.
Now, see, fatigue largely depends on modeling of the fatigue vehicle and the fatigue detail you pick up. So it may be that the strength in steel will not govern. Higher strength steels may be somewhat more susceptible to fatigue. One can't say at the moment, but there's, conclusively, but they are more prone to accumulating fatigue damage, and that has to be guarded, and special care has to be definitely taken on use higher strength steels. So in a way, it is offsetting. When fatigue controls the design, when fatigue is the governing case, you may not need high strength steels at all. They may not be required. That's a true point. Now, speaker has mentioned how the correct design and use of appropriate materials can save carbon footprint. I will just extend the example mentioned, just a comment from someone. Howrah Bridge in FE 250 design weight was 40,000 tons. But with FE 350, it became 26,500 tons. That means it came down by nearly 15,000 tons.
Yes.
Whereas the second Howrah Bridge, it's a cable stayed bridge compared to the oldest one, where the cable stayed design, it became only 16,500 tons. So the same crossing is achieved at a far more carbon friendly manner. And that's very well pointed out by, I don't know who it is, but it is someone in the audience which sums up how technology is moving. Technology, along with time, we have also evolved. The steel is also changing. And today, I think the byword is climate change. Every child born knows what is climate change. That word has been coined in the last 10 years and 5-10 years, and it's become part of everybody's jargon and lexicon on a daily basis. So I think it behoves us to end on this note, this series, keeping sustainability in the larger perspective. As I always say, it's in the Venn diagram, it's the E of the Venn diagram. It's the universe, the outside, and all the other bits and pieces, design, all these little things come in, and they have some intersections in the Venn diagram, the and or ors. But the outer universe, the E is sustainability, in which we are all enshrined. All our work, all our efforts are enshrined in the framework of sustainability always. And that is brought home to us by today's presentation. We had an excellent presentation, and Mr. Ghosh, Professor Siddharth Ghosh gave a perspective on education and the need to create awareness and how to do it by events like this, CPD, education, addressing in curricular change. What the topic is not taught to an engineer at all, where to raise that awareness, school as well as engineering education, how to change it. That is, of course, a professorial discussion he'll have, and he has contributed that in another forum in the World Steel Organization Forum, where all of us were there on that forum. Then I got a wonderful perspective earlier from Mr. Gyana Mohanty, and about the DRI, which is the need of the RS, where to change the technology, the manufacturing side to make the maximum impact. But that involves a lot of capital, a lot of change, and it affects the whole process. It's not easy to shift that easily. The immediate change, as Mr. Vinay Pandey said, is to try and economize the use of steel. Don't over-design. Change the codes as required to do that. Then he also suggests, Mr. Vinay Pandey also suggested that, through good design and through addressing circularity, let's look at and to change the tender documents, the contractual framework, and where we can cause policy change is at least in the design construction phase, from the gate, when the product comes to the gate and needs to get used, and maybe slightly before that during the design phase. There we should address sustainability, because it's a whole of life approach, and in fact beyond life, addressing circularity in reuse and repurpose. So that is the framework of today's discussions and talk. Steel is a winner in many ways, and it is definitely a material with which we have to work. We all recognize what needs to be done. It is now how we all gather together and put our weight behind it and throw our shoulders at the matter. On that note, I finished. Gyana, go ahead.
Dr. Actually, regarding fatigue, I have an observation. I mean, a practice that is followed in the aerospace industries. Yeah, I'll mention about that. I do not know whether we'll be able to use it in business or not. In aerospace industries, what they do is, see, it's a question of reversal of stress. Now, what they do is, in the wings, they short pin it. They create compressive stresses. They create compressive stresses by short pinning the metal. And that increases the fatigue life. I do not know whether we have ever it has been tried or it can be tried.
No, that's what I think, Gyana Mohanty ji, that's what I was talking about, pre-stressing of the, steel itself, that's what I was talking about. I think the way to go ahead is, when you're using the very high tensile steel, perhaps it becomes fatigue sensitive, all right, but pre-stressing it, I think you may overcome that problem of fatigue, that needs to be tried. We'll have to see that. How to
externally pre-stress?
Yes, externally pre-stress.
Like normal pre-stressing.
Normally pre-stress. Yeah,
Venkat, I wrote that code in IRC 20 years or 25 years ago.
But subsequently, in some of the bridges, it has been seen that pre-stressing is all right, but end connections have resulted in loss of pre-stress. That is why many people started dissuaded using it. Right. But this short pinning method increases compressive strength all over the material, not any specially located place.
Yes, it should be done at the manufacturing stage.
Yes.
So, Vinay, is this done, Vinay, at the manufacturing stage? Can we ask for highly fatigue-resistant steels, in specification?
No, actually, it is not done at the level of steel manufacturing. Some of the component manufacturers, suppose in vehicle and automotive, in the clutch, that diaphragm springs, when they manufacture, they do short pinning. So a specific use purpose at SKU level, on a specific component, it is done.
Right.
In fact, in weld joints, the welds are short pinned with manual short pinning hammers. It is done to induce the compressive stress. That is a standard practice in fabricated girders.
Yes. For welding.
Welds are short pinned. Yes.
Well
The
done.
weld joint, the fillet joints are short pitted.
Short pin.
It gives a lot of
Short pin, yes.
advantages.
Right, of course, of course. So thank you for these insights and exchanges of ideas and notes and discussion. I think we're all more equipped and better learned, more learned in this matter of sustainability, and especially in steel bridges and the whole framework that was shown today to us. I don't know if Ruhi, you would like to take over, or?
Sir, I will only propose a vote of thanks.
Thank you, ma'am.
To all honorable dignitaries, it's my privilege to have been asked to propose a vote of thanks for our 6 months webinar series on steel bridges, Day 6, sponsored by JSW Steel Limited. I, on behalf of IIBE, extend a very hearty vote of thanks to all the members and non-members for gracing us with your presence and sharing with us with your valuable feedback and suggestions. Firstly, I would like to thank our managing committee members, our Director General, Engineer DG Diwate. Now, Shriyar Tambe has been newly appointed as our Director General. Our President, Engineer Vinay Gupta, our Treasurer, Dr. Vishal Thomre, our Honorary Secretary, Dr. Gopal Rai, and Engineer Swapnil Joshi for always providing us with the vision for the future of IIBE and for constantly guiding, motivating, and inspiring us to achieve the vision of IIBE. I would like to thank all our eminent executive committee members for their valuable presence and being a strong support to IIBE. I would like to thank our today's speaker, Engineer V.N. Hegde, and our EC member for his enlightening and entertaining presentation and for sharing his valuable knowledge in this platform. I would like to thank our today's moderator, Dr. Harshvardhan Subbarao, also our EC member for managing this webinar. I would like to thank our today's panelists, Professor Siddharth Ghosh and Engineer Gyana Mohanty for sharing his valuable opinion in this platform. I would like to thank Engineer Deepika Singh, Coordinator of IIBE, for always helping and managing all the events of IIBE. Last but not the least, Mr. Huzaffa for all his IT support. And also to all the participants always coming in huge number to make this webinar a great success. Thank you. With the permission, I would like to close the session.
Thank you.
Thank you.
Thank
all.
you. Thank you. Thank you very much.
Thanks again to JSW Steel.
Thank you.
Thank you. Thank you so
Thank
much.
you. Bye.
Thank you.
Bye now.